Today we're going to continue talking about sequences, series, and power series. Remember, we have our one-word definitions of sequences, series, and power series. A sequence is just a list. A series is a sum, and a power series is a function in the form of an infinite degree polynomial. That doesn't make sense. When we plug a real number into our power series, we're not going to get a real number out of it. We're going to get a series. And also, it's not a polynomial if it has an infinite degree. It's a power series. But this is what it looks like. It looks like a polynomial with ... at the end. It just says keep on going. Remember, we're talking about convergence across the board, but it means different things. Jerk move on our part, but it's such a good word for it. A list, we just have to separate the kinds of convergence that we can have, and then it's not a big deal. So a sequence converges if the terms have a limit. We can talk about convergence in the context of sequences. A sequence is the simplest of these constructions. It's just a list, and a sequence converges if the terms have a limit. That is, the limit as n goes to infinity of Sn exists. Remember, a lot of times we'll say something like limit as n goes to infinity of Sn equals infinity, but that statement doesn't make any sense. It communicates what we want, but it's poorly written. So something can't equal infinity. And a limit that tends to infinity doesn't exist. We would say the limit doesn't exist. A sum converges, a series or sum converges if the sum is finite. In the context of a series, we say a series converges if the sum is finite. When we talk about power series, the input is a real number, but the output is a series. So even though it's I'm calling it a function, functions, all of our functions, experience of functions has been input real number, output real number. We do a little bit of input real number, output some other thing. We're mostly going to lean into we plug stuff into it. The input is a real number, but the output is a series. So we have a different question when we're dealing with a function. Sorry, power series. We have a different question when we're dealing with a power series. What real numbers can we put into the series and get a convergent series? So the question when dealing with power series is not, does it converge or not? The question when dealing with a power series is, where does it converge? For what values of the input do we get a convergent series? Because the outputs give us a series. Plug in a real number, it goes from a power series to a series. And we want to know if the series converges. At least we want to know if the sum is finite. If we think of power series as functions, this would be the domain of the function. The stuff that we plug in and get an output that makes sense. We could think of this as finding the domain of our function. Any questions? No, I want to start at one. Couldn't decide which power series I wanted to open with. So here's a power series, x to the n over n. Starting off at 1. X plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4, and so on. We can imagine, since there's an x, that this is some kind of function of x. So we're looking at this as this is some kind of function. So this is a power series. So here we have a power series. If we choose a value of x, then we'll be looking at a series. So what we're thinking of doing is taking our function and plugging in some value. So f of 1. Thinking of our power series as a function and plugging in 1. The output is going to be a series. And when we're looking at a series, the question is this some finite? Does this series represent some real number? That is, does 1 does it make sense to plug 1 into this function? Should we let 1 into the domain of this function? We could plug in some other value. So we just look at the power series as a function where we could plug stuff in. So plug in 0.5 and we get a series. Does it make sense to plug 0.5 into this power series? That is this output series a finite sum? Is it equal to some real number? Note that my question is not, what is this sum? I'm just asking, is this sum a finite amount? A lot of times when we're playing this convergence of series game, someone hands you a series and say, hey, does this series converge? And you're like, oh, yes, that adds up to something. You're like, oh, great, what does it add up to? It's like, well, that's not what you asked. You said, does it converge? And I said, yeah. It's like, oh, but what is it? We're done here. I said it converges. You know what I mean? Classic mathematician. Is this finite? Yep. How much is it? It's finite. That's a pretty wide door to walk through. Got to narrow that down a little bit. All right, it's finite and positive. That actually doesn't narrow down anything. You know, the positive reals and the negative reals and all the reals, those sets are all the same size. That doesn't narrow it down at all by saying it's positive. Yet we feel like we've eliminated half the possibilities. And yet we still have an uncountable infinity of possibilities. That's fucking weird, dude. We can even plug in negatives because we're just trying to figure out what we can plug into this series, power series, and make it make sense. So if I plug in -1, x equals -1. Then we're just going to have like this alternating series. We'll start off with -1, then we'll add 1/2, then we'll subtract 1/3, and so on. The opposite is a series. Does the series converge? Does it make sense? Is -1 allowed in the domain? The instinct that we're trying to build, what we need to do, since when we look at real numbers, we have this sense that we understand what that real number represents. We have to build that for series. We have to be able to look at a series and decide if it converges. So we have to look at these 3 series and say, this series diverges. This series converges. This series converges. And know that right away. Diverges, converges, converges. We have to understand what that means. That this series diverges, which means this sum is infinite. If we keep adding terms to this sum, then it just goes to infinity. This sum will equal some value. No, this sum converges, and we recognize that we want to recognize that it converges absolutely. So it equals one value. There's some value that's the sum of this series. This series down here, it's a little bit weird. You get a sum, but how, depending on how you add up the terms, you can get a different sum. Math's fucking weird, dude. It's possible to have an infinite number of terms that adds up some finite amount. But depending on how you add it up, you can get a different amount. Addition is starting to get really weird. That's not how addition is supposed to behave. We like to believe that addition is always commutative and associative, and we like to believe all these things about addition. But now, once there's an infinite number of terms, it's possible to have the order of the sum make a difference in the outcome. Some addition doesn't matter the order. Some addition, it does. Any questions? This starts off innocuous enough. Sequence, series, power series, list, sum, function. Everybody's all cool with that. But when I start telling you that the addition that you used to believe in, that's the foundation for all of our math, this thing that you believe, well, that's not always true. Question?
So for the y, I don't know. I think that it.
No, there is no end. Once we see this dot, 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 there is no end. Well, that's what we're going to be trying to find out. That's what we're working on. That's just the instinct that we're trying to build. Right now, we don't have it. I do, but y'all don't. You need to see a bunch of series and say these converge for this reason. And then you're like, oh, so this one converges. Nope, that one diverges. So we need to build that experience to build the instinct so that we can see what's going on. Any other questions? So if you're looking at this and saying, I don't see how this one diverges and this one converges, that is correct. I haven't told you. I haven't even prompted you to maybe even read about that. So it's new. It's okay. You don't know yet. Just like that first day in math class where your teacher wrote all the digits on the board. And you say, if there's a 2, there's a 3, you put a plus in between it, it becomes 5. You're like, oh, what? What is all this craziness? It's like, well, then you start doing multiple digits. And you're like, oh, wait, what? So if I have the 7 plus the 8, it's a 15, but I put the 5 down here and the 1 way up top. Well, all right. The difference is you were kids back then and you're generally more accepting of things. Now you're adults and your natural response when I say something weird is to be like, oh, no. I learned that one when I was a teenager. No, I'm not going to do what you tell me, old man. We don't need no education. So yeah, we're not really sure. What is it that I'm looking at that y'all aren't looking at? That's what we're trying to build. I wanted to start with power series, even though we don't have a strong foundation for it, because I want you to see the whole picture. That's why yesterday we talked about power series can be used to represent functions. Either a function that we know that we want to represent with some polynomial, or some function that we don't know, and we create a power series for a model. Right. So there's not only stuff to learn. You don't just learn about these objects. You also have to learn about the culture that we built up around these objects. The way that we write things, the symbols that we use, the style of writing things. After you all graduate with your degrees in math and go to grad school and you get your master's degree, your PhDs in math, you start to use the word thus and therefore anymore. And people will think, you're really weird. Why do you keep saying thus? Are you Mr. Burns from The Simpsons? Which I think is good, which is why I recommend we all use twice, but after that we just switch to 3 times. We got to bring back thrice. And you got to say it that way with some style. Thrice. Anyway, what are we talking about? Convergence of series. So we're generally going to use summation notation to represent a series. So we'll say something like, let AN be a series. And we're leaving off some information. I'm just going to write a sigma and then AN, name of the terms. I'm also not going to write my sigmas this well. They're just going to start looking like backwards 3. The limit as time goes forward of my sigmas equals backwards 3. But notice I'm not telling you where to add up. When you just write sigma AN, we're going to read this as an infinite series. So we're going to read this as going to infinity. We're going to read it as an infinite series. That's going to be our shorthand for an infinite series. Notice I did not include the n equals. The aforementioned laziness is trying to get me to write as little as possible. But when we write sigma notation, we should tell the reader what values of the index. Where do we start? But because our series is going to infinity, we don't really care about where it starts. We care that it's going to infinity. And if we're studying what happens in infinite series, we can get away with a shorthand. Does that make sense? The starting value just needs to be something that makes sense. As long as the starting value makes sense in all the terms, as it's defined, the term is defined for all the values of the index, then where we start is irrelevant. What happens is the infinity part. The infinity part is the important part. As long as our start just makes sense, then that's what we're worried about. This one's only not okay because I can't plug 0 into this term. So if we're writing indexing, we want to make sure that our indexing is okay, that all of our values are going to be defined. Ultimately, we're looking at infinite series. We have an infinite number of terms. Where the terms start is less important than the terms going to infinity. The start doesn't matter for the convergence. If you have an infinite number of terms, if you cut off one term, no one will notice. The thing is, if you have an infinite number of terms, you can cut off 1,000,000 terms and no one will notice. There's an infinite number of terms. I could cut off 10 to the 31st terms and no one would notice because of the infinite number of terms. Any questions? Mathematicians have certain ways of doing things. I don't know if you've heard this phrase applied to math before, but the phrase is brute force. This is just when you push through the problem with power. Apply a computing problem to the power, you're using brute force. On the other end of this spectrum would be an elegant solution. That's a super mathy word. Mathematicians like their elegant solutions. And you should say it all fancy like that. Mark yourself as a mathematician using the word elegant rather than just some normie using the word elegant. You know what I mean? Here's one of the things that's comforting, especially in an age of massive computing power in our pockets. One way to determine if a series converges is by looking at its sequence of partial sums. So let's let AN be a series. We're going to see that shorthand. A series converges if its sequence of partial sums converges. At this point, you might be thinking, yo, you have not even talked about sequences. And I'll be like, well, I said that a sequence converges if the terms have a limit. So I said what I need to say about it. But I didn't need to talk about this particular sequence. It's a thing that a sequence that belongs to a series. So we're going to be making a list. Apparently, we're going to be making a list of partial sums. So I'm going to start with A1. The next term is going to be A1 plus A2. The next term is going to be A1 plus A2 plus A3. And we're really just saying, what happens if we add the next term? We're just figuring out what happens to the next term, or what happens if we just add the next term to what we have so far. We know that this sequence converges if the terms have a limit. So if doing this process, if just continually adding the next term is headed towards some limit, then we would say that the sequence converges. And since this is a sequence of partial sums, that means the series converges. Moreover, the limit of the sequence of partial sums is the sum of the series. The limit of the sequence of the partial sums is the sum of the series. Any questions? At this point, we do not have a lot to go on. We're trying to cover a lot of stuff all at once because I want to start with the big picture. What we have now is a mechanical way to determine if a series converges. I look at my calculator on my desk and say, I'm not going to need that today. And then in the back of my mind, I thought, sequence of partial sums is today. And I go, out the door we go. Don't get old, kids. So what we have here is a mechanical way to determine if a series converges. Questions? The one that I was going to do converges too slowly anyway, so I don't know what I'm worried about. Here is a specific series. Write down the terms of this series. So the first term is going to be 3 times 0.1 to the 0 power, so that's just 3. And then 3 times 0.1 to the negative 1 to the 1. Oh, I want negative that. This is why I have to write down the terms whenever I write down a series. Change entirely the problem, and I'll drop a negative. So 3 times 0.1 to the negative 1. Oh no, I made it 0.1. Jeez. Don't get old, kids. Your audibles start to suck. I have 0.1, not 10. Now I'm not going to get anything right. This happens to me in game. If I fail the first roll of the session, I'm going to fail almost all the rolls of the session. It's like if the first roll of the session, especially if it's for something that doesn't matter. So first roll of the session, if that's less than 10, every roll is going to be less than 10. That's when we immediately start to avoid fights. Like, all right, we're going to have to avoid encounters like crazy because Leech is not going to make any rolls today. I also have the false hope curse. If my first roll is a crit, I won't make anything else the rest of the night. So I don't have as powerful a curse as Will Wheaton has, but it's pretty strong. There's that false hope. Incidentally, I will only crit the first roll of the session if it just doesn't matter. I would like to do a survival check to look for something. Tracks. The DM's like, oh, there aren't any tracks, but he has me roll anyway. I'm going to roll a 20 on that. No, 20. Well, there aren't any tracks. I told you that this was uninhabited. What are we talking about? My inability to keep track of my own examples. So I picked this because it's very clear what this series is going to add up to. It's very clear that this series converges, and it's very clear to what it adds up. But we need to look at the sequence of partial sums for this series to help us reinforce that note of the brute force technique for determining if a series converges. But we were not meant to do this example because I got distracted. I called the audible at the beginning. I'm going to start at 0 instead of starting at 1. And then it was all over at that point. All right, that's going to do it for today. I will see y'all on tomorrow. Thanks.